You think you understand atoms. You probably picture them the way everyone does. A tiny, dense nucleus sitting at the center. Protons and neutrons packed together like marbles in a bag. Electrons buzzing around in orbits like planets around a sun. It's the image you've seen in every textbook, every science documentary, every classroom poster since you were a child. Here's the problem. That picture is not just incomplete. It's catastrophically wrong in a way that, if you actually believed it, would make the existence of every atom in the universe, including the ones in your body right now, physically impossible. Richard Feynman knew this, and he spent a good portion of his career trying to get people to see just how deeply broken our intuitions about the atomic nucleus really are, because hidden inside that tiny cluster of protons and neutrons is a paradox so severe, so violent, that by all rights, every nucleus should explode in a fraction of a second. They don't. You exist. Matter is stable. So what's going on? Let me show you the problem. Take your hand and look at it. In every atom of every molecule in your skin, there's a nucleus. Let's pick a simple one. Carbon. 6 protons, 6 neutrons, all crammed together in a space about 10 femtometers across. That's 10 millionths of a billionth of a meter. Unimaginably small. Now here's what you need to understand about those 6 protons. They all carry positive electric charge, every single one. And positive charges repel each other. You learned this in grade school, like charges push apart. It's one of the most basic facts of electromagnetism. But let me tell you how hard they push. The electromagnetic force between 2 protons at nuclear distances, we're talking about forces on the order of 100 newtons. 100 newtons. That might not sound like much. After all, you can push on a wall with 100 newtons of force pretty easily. But now remember, we're talking about the force acting on a single proton, a particle with a mass of 1.67 x 10^27 kilograms. If you do the calculation, if you work out what acceleration that force produces, you get something absolutely absurd. We're talking about accelerations of 10 to 28 meters per second squared, 10 octillion meters per second squared. To put that in perspective, if that proton were free to move, it would reach the speed of light in less than a trillionth of a second. So here's the question that should be keeping you up at night. Why doesn't the nucleus just explode? You've got 6 positively charged particles crammed into a space smaller than a virus, all pushing away from each other with forces so enormous they should scatter across the room at essentially the speed of light. And yet nothing happens. The carbon nucleus sits there, perfectly stable for billions of years. This is the misconception Feynman wanted to destroy. The idea that the nucleus is just a simple cluster of particles held together by some vague nuclear force that you don't need to think about too carefully. Because if you do think about it carefully, you realize that what's happening inside every atomic nucleus is not peaceful coexistence. It's a war. Let's talk about what's actually holding these protons together. Because it's not enough to just say there's a strong nuclear force. That's like saying airplanes fly because of lift. True, but it doesn't explain anything. The strong nuclear force, the actual quantum chromodynamic force between quarks mediated by gluons, is bizarre in a way that has no parallel in everyday experience. Here's what makes it different from every other force you're familiar with. First, it's strong. Obviously, it has to be. It has to be strong enough to overcome that electromagnetic repulsion we just calculated. In fact, at distances of 1 femtometer, the strong force is about 100 times stronger than the electromagnetic force, 100 times. That's why we call it the strong force. But here's the catch, and this is where the misconception lives. The strong force has a range, a very, very short range. At distances beyond about 1.5 femtometers, it essentially vanishes. It doesn't just get weaker like gravity or electromagnetism, it disappears. It's as if the force just gives up. Think about what this means. You've got these protons and they're about 1.7 femtometers across. When they're touching, when their quarks are close enough, the strong force dominates, it's overwhelming. But if they get pulled apart by even a tiny amount, maybe 3 femtometers, maybe 4, the strong force drops to essentially zero, and all that's left is the electromagnetic repulsion. This is not a stable situation. This is like balancing a pencil on its point. The slightest disturbance should send everything flying apart, and yet it doesn't. Here's where we need to go deeper, because the answer to why nuclei don't explode isn't just about forces. It's about something far more subtle, far more strange. It's about the fundamental quantum mechanical nature of matter itself. Stop and consider this. What is a proton, really? When you get down to it, when you strip away all the classical intuitions, a proton is not a little ball. It's not a marble. It's a quantum wave function. It's a probability distribution spread out over space. And that distribution has a characteristic size, a scale over which the proton's wave function extends. Now comes the crucial part. The Heisenberg uncertainty principle tells us that the more you confine a particle in space, the more uncertain, the higher its momentum becomes. This isn't just a limitation on measurement. This is a fundamental property of what it means to be a quantum particle. When you squeeze a proton into a tiny nuclear volume, you're confining its wave function. You're reducing the uncertainty in its position. And the universe responds by increasing the uncertainty in its momentum, which means on average the proton is moving fast, really fast. We're talking about typical velocities on the order of 10% the speed of light. These protons are not sitting still. They're ricocheting around inside the nucleus like bullets in a steel box. And every time they bounce off each other, every time their wave functions overlap, there's this absurd quantum mechanical dance between the strong force trying to hold them together and their kinetic energy trying to blow them apart. The nucleus is not a static structure. It's a seething, dynamic, quantum mechanical system balanced on a knife edge. Let me tell you why this matters, why this isn't just some technical detail for particle physicists to worry about. The misconception, the big lie that Feynman wanted to expose, is the idea that we can understand the nucleus the way we understand ordinary matter, that we can think of protons and neutrons as distinct, separate objects that just happen to be stuck together. This is wrong at every level. Inside the nucleus, the very concept of separate particles starts to break down. The wave functions of neighboring nucleons overlap significantly. They're constantly exchanging virtual pions, constantly swapping quarks and gluons through the strong interaction. The nucleus is not a collection of distinct particles. It's a collective quantum state. A single unified wave function that just happens to contain several chunks of concentrated charge. And this has consequences, real, measurable consequences. For instance, the mass of a nucleus is not the sum of the masses of its protons and neutrons. It's less, significantly less. A helium-4 nucleus, 2 protons, 2 neutrons, weighs about 0.7% less than the sum of its parts. That missing mass, that mass defect, represents the binding energy of the nucleus, the energy that's been extracted from the system by forcing those nucleons into this quantum mechanical bound state. Where did that mass go? It was radiated away when the nucleus formed, released as energy. E-NOS MC2, that missing mass is energy. And if you add it all up, if you calculate the total binding energy of all the nuclei in your body, you're talking about energies equivalent to thousands of nuclear weapons. You are, in a very real sense, held together by the energy of nuclear binding. Every atom in your body is a tiny bomb that never goes off. But wait, let's push this further, because there's another layer to this misconception, another way our intuitions fail us. If the nucleus is this precarious quantum system balanced between explosion and collapse, why are some nuclei stable and others aren't? Why does carbon-12 sit there forever while carbon-14 decays with a half-life of 5,630 years? Why is uranium unstable, prone to splitting apart or spitting out alpha particles, while iron is essentially immortal? The answer has to do with something called the semi-empirical mass formula, sometimes known as the Bethe-Weizsäcker formula. And it reveals something profound about the nuclear force. You see, as you add more protons to a nucleus, two things happen. First, the electromagnetic repulsion grows, and it grows fast, because every proton repels every other proton. Add one more proton to a nucleus with Z protons, and you've added Z new repulsive interactions. That's a quadratic growth. The repulsion scales like Z2, but the strong force doesn't work that way. The strong force only acts between neighboring nucleons. It has that short range, remember? So when you add a new nucleon, it only binds to the nucleons it's actually touching, maybe 8 or 10 of them. The binding energy grows roughly linearly with the number of nucleons. Do you see the problem? For light nuclei, the strong force wins. The binding energy dominates. But as you go heavier, as you add more and more protons, eventually the electromagnetic repulsion catches up. Eventually you reach a point where adding more protons makes the nucleus less stable, not more. This is why there's no nucleus with 200 protons. This is why the periodic table ends. Beyond uranium, beyond plutonium, you run into a fundamental limit. The electromagnetic force, growing quadratically, eventually overwhelms the strong force, growing linearly, and the nucleus tears itself apart. Iron 56 sits right at the sweet spot, the point of maximum binding energy per nucleon, the most stable nucleus in the universe. Everything heavier than iron wants to decay toward iron. Everything lighter than iron wants to fuse toward iron. Iron is the bottom of the nuclear energy well. Stars know this. When a massive star runs out of fuel and starts fusing silicon into iron, that's it. Game over. There's no more energy to be extracted. The core collapses. The star explodes, all because of this balance, this knife-edge equilibrium between forces. Now let me tell you something that might surprise you. For all our understanding of nuclear physics, for all our sophisticated quantum chromodynamic calculations, we still can't predict nuclear properties from first principles. We can't take the standard model, plug in the masses and charges and quantum numbers of quarks, and calculate the exact binding energy of carbon-12. We can't do it. The math is too hard. The quantum chromodynamic equations are nonlinear, strongly coupled, impossible to solve analytically. Instead, we do something clever. We use models, approximations. The liquid drop model, which treats the nucleus like a droplet of incompressible fluid. The shell model, which treats nucleons like electrons in atomic orbitals. These models work. They make predictions that match experiments, but they're not fundamental. And this is Feynman's point. When we talk about understanding the nucleus, what do we really mean? We have models that describe its behavior. We have equations that match the data. But do we understand why the strong force has the properties it does? Do we understand why quarks come in 3 colors, why gluons are massless, why the coupling constant has the value it does? No. We describe, we calculate, we predict, but at some level we reach the boundaries of explanation. We reach the point where the answer to why is simply because that's what the universe is like. Feynman understood this. He understood that science is not about replacing mystery with certainty. It's about replacing one kind of mystery with a deeper, more precise kind of mystery. But here's the thing, even without perfect understanding, we can use this knowledge, and we do every day. Consider nuclear magnetic resonance, NMR, the same physics that keeps atomic nuclei stable, the same quantum mechanical properties of nuclear spin, the same magnetic dipole moments arising from the angular momentum of protons and neutrons allows us to image the inside of your body without cutting you open. An MRI machine works by exploiting the fact that protons in hydrogen nuclei have spin, quantum mechanical angular momentum. When you put these nuclei in a strong magnetic field, their spins align. Then you hit them with radio waves at just the right frequency, and you can flip those spins, make them precess, and measure the energy they release as they relax back to equilibrium. The frequency depends on the local chemical environment, on whether that hydrogen is in water or fat or protein. And by measuring those frequencies across a three-dimensional volume, you can reconstruct an image. You can see tumors, blood clots, torn ligaments, all because of the quantum mechanical properties of the atomic nucleus. Or consider nuclear power. Every watt of electricity from a nuclear reactor comes from the same binding energy we talked about earlier. You take a heavy nucleus, uranium-235, and you split it into two lighter nuclei. The products have more binding energy per nucleon than uranium, which means energy is released. Mass is converted to energy. E in mass, mc2. The energy that lights your house, that charges your phone, that runs the hospital, keeping someone alive. That energy comes from the strong nuclear force, from that same quantum chromodynamic interaction that holds protons together against electromagnetic repulsion. We've turned the nuclear paradox into technology. Let me take you even deeper, because there's a sense in which understanding the nucleus is understanding the universe. Every element heavier than helium was forged in the core of a star or in the fireball of a supernova. The carbon in your bones, the oxygen you breathe, the iron in your blood, these elements exist because at some point in some stellar furnace billions of years ago, nuclei were smashed together with enough energy to overcome that electromagnetic repulsion and fuse into heavier elements. The universe started with hydrogen, just protons. After the Big Bang, after the cosmic microwave background decoupled, we were left with a universe that was about 75% hydrogen, 25% helium, and trace amounts of lithium. Everything else, every element in the periodic table from carbon to uranium came later from stars. And the process that makes those elements is nuclear fusion, which is just another way of saying taking nuclei, smashing them together hard enough that the strong force can grab hold and creating a new, heavier nucleus. But there's a limit. Remember iron? Iron-56, the most stable nucleus. You can't extract energy by fusing anything heavier than iron. The binding energy curve turns over. Past iron, fusion costs energy instead of releasing it. So where do the heavy elements come from? Gold, platinum, uranium, they come from supernovae, from neutron star collisions, from cataclysmic events where there's so much energy sloshing around that the universe can afford to create nuclei that are less stable, that sit higher up on the binding energy curve. The gold in your wedding ring is supernova ash. The uranium in nuclear fuel rods is the remnant of stellar death. All of this, the entire chemical complexity of the universe, emerges from the properties of the nuclear force, from that short-range quantum chromodynamic interaction between quarks. Here's what Feynman wanted you to feel, not just to know, but to feel. Every atom in your body contains a nucleus, a tiny femtometer-scale region where the rules of everyday experience completely break down, where particles move at relativistic speeds, where forces strong enough to accelerate particles to near light speed in a trillionth of a second are locked in eternal combat with electromagnetic repulsion, where quantum mechanics reigns supreme and the very concept of separate particles becomes meaningless. And yet, this is not chaos. This is not disorder. It's precisely because the nuclear force has the properties it does, precisely because it's strong but short range, precisely because it saturates, precisely because it has that delicate balance with electromagnetism, that stable nuclei exist, that atoms exist, that chemistry exists, that you exist. If the strong force were just a little weaker, nuclei couldn't form. The electromagnetic repulsion would win. The universe would be nothing but hydrogen. If it were a little stronger, everything would fuse into iron immediately after the Big Bang. No stars, no galaxies, no life. We live in a universe balanced on a knife edge. And the sharpest point of that knife is inside the nucleus. So why does this matter? Why should you care about the internal dynamics of something 10 million billion times smaller than a grain of sand? Because this is what understanding actually means. Most people are familiar with atoms. They've seen the diagrams, heard the words. But familiarity is not understanding. Familiarity is comfortable. Understanding is uncomfortable. Understanding demands that you confront the places where your intuitions fail, where your mental models break, where the universe refuses to behave the way you think it should. Feynman spent his life trying to get people to see the difference, to see that the goal of science is not to make nature fit our preconceptions, but to expand our minds until we can hold the true strangeness of reality without flinching. The nucleus is not a cluster of marbles. It's a quantum mechanical bound state teetering on the edge of existence, held together by forces we can describe but not fully explain, exhibiting behaviors that emerge from the deepest laws of physics we know. And once you see that, once you really internalize the violence, the improbability, the sheer quantum weirdness of what's happening inside every atom, you can never look at matter the same way again. You're not made of stuff. You're made of process, of forces and fields and quantum fluctuations locked in dynamic equilibrium. You're not solid. You're mostly empty space held together by the electromagnetic interaction between electron clouds. But at your core, in the nuclei of your atoms, there's something even stranger. A place where the universe is playing with fire, where matter exists only because the strong force is willing to fight an endless war against electromagnetic annihilation. And the fact that you exist, that you can think about this, that you can understand it, even partially, even imperfectly, is perhaps the most remarkable thing of all. That's what Feynman knew. That's what he wanted to teach. Not facts, not formulas, but awe, wonder. The recognition that we live in a universe stranger and more beautiful than we ever imagined. And that understanding that strangeness, confronting that beauty, that's what makes us human.